If I'm looking at substitution, let me write these guys down. Y equals a negative 2x plus 3, and the negative x plus 1/2 y equals a negative 1. This one is already set up pretty nicely for substitution. That first equation is already solved for y, so I'm going to take this y value and plug it in right here for y in my second equation. So I've got negative x plus 1/2 times a negative 2x plus 3 equals a negative 1. And then from here I distribute the 1/2. Multiplying by fractions isn't bad, so I probably wouldn't eliminate the fraction just yet. So here I'm going to get a negative x plus 3/2 equals a negative 1. I combine like terms, that's a negative 2x plus 3/2 equals a negative 1. And then from here I can subtract that 3/2 from each side, but again, it's more work to get common denominators than it is just to multiply everything by 2. So when you do that, you get a negative 4x plus 3 equals a negative 2. And now I subtract the 3 from each side. So I get a negative 4x equals a negative 5. We can already kind of see where we're going with this. Divide each side by the negative 4. And this is good news because I've gotten exactly what I got when I did elimination. I've got a positive 5/4. Okay, I still have to plug it back in and check it to find y. So I've got y equals negative 2 times 5/4 plus 3. Here, when I do this, this is over 1. I can reduce the negative 2 to a negative 1 and a 2. That gives me a negative 5/2 plus 3. And from here, you can get common denominators. But again, if you don't feel like getting common denominators, multiply through by 2 and watch what happens. 2y equals a negative 5 plus 6. And now I can combine like terms. That's a 1. Divide each side by the 2. And I find out once again that y equals 1/2. Okay? So now with absolute certainty for this particular problem, I can say that my ordered pair here is 5/4, 1/2. It matches what I have on the graph, it matches what I got with elimination, and it matches what I got with substitution. Okay? And then as far as the best method for this one, obviously it's anything but graphing. You could make a case for elimination and say when you rearranged it, you already had additive inverses in front of the x, or you could make a case for substitution and say that it was already solved for y. So for this one, I would say substitution or elimination, and you can easily defend either one of those. Okay? When I look at the next one, number 9, we have to graph each of these. If we think about the linear portion of this thing, again, the linear portion of this thing is like y equals a negative 2x plus 3. And then the linear portion of this guy is y equals an x minus 2. So I graph each of those in terms of a line. So I've got the 3, and I've got the negative 2 for my slope. That's this first one. Since there's no equal to condition in this first equation, or this first inequality rather, I'm going to use a dotted line. So I use a dotted line. For the next one, I've got a y-intercept of negative 2 and a slope of 1. So that's up 1 over 1, up 1 over 1. Since there's an equal to condition, I'm going to use a solid line for this one. And now I just have to figure out where I'm going to shade. I want it to be below the first line and below the second line. So it looks like this is the section that they're going to have in common down here. But I just choose a point to make sure. So I pick a point like negative 3, 0. Or sorry, 0, negative 3. And if I plug in 0, negative 3 for this first equation, I plug the negative 3 in for y, the 0 in for x, and I find out that negative 3 is less than 3, which is true. If I plug the negative 3 in for y here and the 0 in for x, I find out negative 3 is less than or equal to negative 2, which is also true, which since it's true for each of those, this is the section I'm going to shade. Okay? And then the last thing I should technically do is any solid line that's not touching the shaded region should technically be a dotted line or get erased completely. Okay? For the next one, I do essentially the same thing, but now I don't have this in the proper format. This one I would probably subtract the 1 from each side to get y is less than or equal to a 2x minus 1. Now that's in slope-intercept form. For the first one, I would either do the intercepts. If you plug a 0 in for y, you find out that x equals a negative 3. Plug a 0 in for x, you find out that y equals 6. That's one way to go. Or you can rearrange this thing, add the x to the other side, and then multiply by 2, which gives you a 2x plus 6. Okay, either way should be fine. But when we graph this, I've got a -1 and a slope of 2 for the first one. For the second one, whether I use the x and y intercepts, which are the -3 and the +6, or whether I start with the 6 and do a slope of 2, I'm going to get the same thing. Okay? But what I have here this time is I have parallel lines. Oh, and I forgot to look at whether it was solid or dotted. This one should be a dotted line because there's no equal to condition. And now I look for where I'm going to shade this thing. I want to be less than that first line, which puts me down here. But I want to be greater than the other line, which puts me up here. So it looks like these aren't going to overlap. And what I can do is I can choose a point from each of these sections and test them. And if I do that, I'm going to find out that none of them work, which means this one is actually no solution. Okay? Which means I'm not going to have anything in my graph. I guess I could erase this guy or turn it into a dotted line. But really, the answer here is no solution because none of them worked. Okay? If I look at the next one, I'm looking at this feasible region. I want to state the vertices. Remember, those are the corner points of this shaded region. So the first one looks like 1, 0. The next one looks like 1, 4. The next corner point looks like 5, 4. And the last one looks like 4, 0. Okay? So those are my vertices, those are my corner points. And now if I'm given an objective function and I want to find out what's the maximum and minimum, I just plug each of these values in. I plug the 1, 0 in for x and y. And when I do that, I get a 1 out for h. That's a terrible looking h. Let me try again. So I find out that h equals 1. I do the same thing with the next one. I plug the 1, 4 in. When I do that, I get 1 minus 8, which is a -7. That's my h value again. I should keep writing h. There we go. The next one, the 5, 4, I'm going to plug that one in. When I plug the 5 in for x and the 4 in for y, that's 5 minus 8, which is a -3. And then the last one, the 4, 0, I plug that in, and that's going to give me an h value of 4. So now when I talk about maximum or minimum here, my maximum this time is when h equals 4. And my minimum is when h equals a -7. And this one was actually reversed to what we might think. The highest point gave me the lowest value, and the lowest point gave me the highest value. Okay? For this one, we're going to graph the feasible region ourselves. So I'm given some constraints, and I'm just going to graph these. The first one, x is greater than or equal to 0. That's the equation of a vertical line when we look at x equals 0. And it's the vertical line that goes right here. Okay, it's actually my y-axis. If I look at x equals 4, that's the vertical line that goes right here. That is a terrible looking vertical line. Let me try that again. I cannot live with that. There we go. That's much better. The next one, the y is less than or equal to the 1/2 x plus 3. So I go to a y-intercept of 3, and then it's got a slope of 1/2, up 1 over 2, up 1 over 2. I draw the best line I can. The next one, I've got a y-intercept of 3 and a slope of -1/2, which looks like this. Once again, I draw the best line I can. And what happens here, just like my system of inequalities, this graph is split into many, many different pieces here. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces. Okay? And when I look at being greater than that first vertical line, greater than that line means I want to be to the right of it, which means it's not going to be sections 1, 2, or 3. So I'm going to kind of narrow it down. I want to be less than the line y equals 4, which means I want to be to the left of that, so that eliminates sections 7, 8, and 9. And then I want to be less than that first line I drew that had the positive slope, which eliminates section 4 because I have to be below that line. Then I want to be greater than the line with the negative slope, which narrows it down to section 5. Okay? And once again, I could pick a point and plug that in to test that, and I'll find out that this is the section I want to shade. Okay? So that's my feasible region. And when I look at this feasible region, I want to identify my vertices of the feasible region. The first one I have looks like 0, 3. The next one I have looks like 4, 5. And then the last one I have looks like 4, 1. And once again, I want to take my objective function. I'm just going to plug these values in. When I plug the 0, 3 in, I find out that c equals 3. When I plug the 4, 5 in, I find out that c equals 9. And when I plug the 4, 1 in, I find out that c equals 5. So my maximum where it is the 4, 5. Okay? What it is the value of 9. The minimum where it is the 0, 3. What it is the value of 3. Okay? When I look at this last one, I've got a system of 3 equations. You can solve this by substitution or elimination. Personally, what we're typically going to do, and what's usually easiest, is to just go with elimination. Eliminate one variable, but you got to do it twice. And then you'll be left with a system that only has 2 equations, 2 variables. So I either have to eliminate x, y, or z. I'm going to go with y this time. So I'm going to take those first 2 equations, the x plus y plus z equals 3, and the x minus y minus z equals 5. And I'm going to add them up, okay? Because they already have additive inverses in front of the y values, so I end up with 2x. The y values eliminate, and by a happy accident here, the z values eliminate also, which gives me an 8. So now I can just solve what's left for x. I divide each side by the 2, so I find out that x equals 4. I still need another equation where y has been eliminated, and I used these first 2 already. So now I have to use this third equation in some way. So I'm going to take the x plus y minus z equals 1. And I want to eliminate y, so I'm going to use that second equation because it already has additive inverses. And I'm going to add them together. So I add them up, and I end up with 2x minus 2z equals 6. Okay, and now I have a second equation, but I also already have an x value that I can plug in. So I plug in the 4 for x, and now I can easily solve for z. I get 8 minus 2z equals 6. I subtract the 8 from each side. So the negative 2z equals a negative 2. Divide each side by the negative 2. And I find out that z equals a positive 1. But I'm still not finished. I've got my x value. I've got my z value. I still need to find y. So I'm just going to use probably that first equation. Why not? X plus y plus z equals 3. I plug in what I know. I know that x is the 4. I know that z is the 1. So now I combine like terms. Y plus 5 equals 3. I subtract the 5 from each side. And I find out that y equals a negative 2. Okay. Now I have all 3 variables. So now I've solved the system. I'm going to write this as an ordered triple. Remember, it's my x value, then my y value, then my z value. Okay. I hope this was helpful, and good luck on your test.